in a very original way, namely by giving it the Bell experiment. So in the Bell experiment we have two observers, Alice and Bob, and each of them can make a choice between two possible measurements, and each of these measurements has two possible outcomes. Okay, if we have this kind of situation, and we can make a table of all probabilities of the possible joint outcomes. So for example, Alice picks measurement A and Bob picks measurement B prime, and then we can look at the probability that certain outcomes, and that gives this table. And the famous property about this experiment is that this setup is not realizable in classical probability theory. So you cannot devise an experiment using just classical probability theory that would give exactly these probabilities as outcomes. So that's basically it follows from the Bell inequalities. But it is realizable in quantum mechanics. So there is a setup in quantum mechanics that produces exactly these probabilities. So now the goal of this talk will be to develop systematic techniques to study whether a certain setup is classically realizable. So of course we have this Bell setup, but we want to, here you can check directly that it's not realizable, but we want to have some general techniques. So if you have any number of observables and any probability table, you want to know whether it's realizable or not. Okay, so there are already several techniques that have been developed recently. So the first one of these is by Abramsky and others. So they gave a topological model of these kind of Bell-type scenarios. And if you have this topological model, then you can look at the cohomology groups of the space associated to a certain measurement cover. So this is what Cohe explained on Monday. So cohomology groups are certain mathematical structures that can be assigned to many things in mathematics, like topological spaces, but also other structures, and they provide certain information about a space. And now if you have a certain set of measurements, like a Bell-type scenario, then you can associate a topological space to it, and then you can associate cohomology groups to this space. And these cohomology groups tell you whether it's classically realizable or not. It gives you certain criteria. Well, and another model that has recently been considered by Sam Staden and Sander Uyden is the model of effect algebras. So they show that in the world of effect algebras, you can also give a characterization of whether something is classically realizable or not. So now we can wonder, can we also define cohomology of effect algebras, and in such a way that we also obtain a cohomological criterion for realizability. So that's what we will try to do in this talk. So the outline is very simple. First I will say a few words about effect algebras. Then I will define their cohomology and look at some of the mathematical properties. And finally we will apply it to Bell-type scenarios. Okay, so what are effect algebras? We've already seen them in Duško's talk yesterday, but I'll briefly summarize it. So effect algebras are an algebraic model of quantum logic, just like Boolean algebras are an algebraic model of classical logic. Well, a key feature of quantum logic is that it should be partial. So, for example, conjunction is not always defined. We have two properties like this. So we have a particle P, and we can make two properties. So the particle is at a certain position, and it has a certain momentum. And then if we look at the conjunction of these two statements, we could say that this conjunction is not defined, because we cannot measure these two statements simultaneously. So that's why we want the conjunction in our logic to be partial, unlike what we would have for Boolean algebras. And effect algebras are defined using such a partial operation. So an effect algebra consists of a set and a partial binary operation on this set. And furthermore we have constant 0 and 1 representing the minimal and the maximal element in the logic. And also we have an orthocomplement operation, so this is like a negation in the quantum setting. We have the following properties. So the partial operation should be commutative. So for partial operations there's a certain subtlety involved. So here commutativity means that whenever x plus y is defined, then also y plus x is defined, and these two are equal. So the subtlety of course becomes the partiality. And associativity is defined in a similar way, and we want that 0 is the neutral element. Furthermore, the orthocomplement operation should really behave like a complement. So if you add something to its complement, then we get 1. And also a complement should be the unique element with this property. Furthermore, the complement of 0 is 1. That's the easy property. And finally, we have a property called the 0-1 law. It says that if a plus 1 is defined, then a should be equal to 0. So what this is basically saying is that 1 is like a maximal element, because addition with the maximal element is almost never defined. Okay, so some examples of effect algebras. They mostly represent measurements in quantum mechanics or in classical mechanics, or probabilities. So the simplest example is the unit interval within the real numbers, so all numbers between 0 and 1. And we can make this into an effect algebra by taking partial addition as a binary operation. So addition of two numbers in 0, 1 is not always again a number in 0, 1, so that's why we will have only a partial operation. So it defines if and only if the sum of the two numbers does not exceed 1. And the complement can be defined as 1 minus a. And then you can easily check that this satisfies all the properties of an effect algebra. And this is one of the motivating examples. It represents probabilities, because the unit interval is in fact a set of probabilities. Then the second example, if we have a Hilbert space, then we can look at all operators lying between 0 and 1 in the standard ordering of operators on a Hilbert space. And this forms an effect algebra in very much the same way, using the same kind of operations. And this is also one of the basic examples, because this one represents unsharp quantum measurements. So it's a generalization of the projections on a Hilbert space. Finally, we also have a model of classical measurements. So in measurements in classical logic are modeled by a Boolean algebra. And if we have a Boolean algebra, then it forms an effect algebra if we take as an operation the disjoint union. So disjoint union means that the operation is defined if and only if the intersection of the two elements is 0. And in that case, the sum is defined as their union. So the operation here is disjoint union. So not only classical measurements, but also, not only quantum measurements, but also classical measurements form an effect algebra. So you can see that's a generalization of Boolean algebras. And finally, any orthomodular poset is also an effect algebra. So for example, it's the projections on a Hilbert space. And the structure is defined in very much the same way as we would do for Boolean algebras. Okay, so effect algebras can be seen as something that models either probabilities or classical measurements or quantum measurements. So if we have measurements, then we usually also want to have a model of states on a quantum system, because those are two of the basic building blocks of quantum mechanics. We have states and observables or measurements. And we've modeled measurements as effect algebras, and in the same way we can associate a state space to each effect algebra that models the right notion of states. So the state space consists of effect algebra morphisms from our effect algebra into the unit interval, so the set of probabilities. So you could say that it's a kind of generalized probability distribution, because it assigns a probability to each measurement in a consistent way. And saying that it's a morphism means that it preserves addition whenever the addition is defined, and it preserves the maximal elements, and then it automatically follows that it preserves all of the structure in the effect algebra, so also the 0 and the complement. Okay, so let's look at an example. So if we have the power set, which is a finite Boolean algebra, then we can look at the state space. So the state space should assign to each element of the power set a number in the unit interval. And it should also preserve addition, but if we have an element of the power set, so subsets of an n-element set, then it's always a union of singletons. And because this morphism should preserve unions, it is in fact determined by its values on singletons. So a state on the power set of n is determined by n numbers in the unit interval. And the condition that 1 should be sent to 1 means that if we take the union of all those singletons, then we get the entire set, and this one should be sent to 1. So a state on the power set of n should consist of n numbers whose sum is equal to 1. And this is actually a standard probability distribution on n elements, or geometrically it is a standard simplex. So the state spaces are standard simplexes, so that are points, lines, triangles, tetrahedra, and higher dimensional generalizations of this. So a second example, if we take the effects on a Hilbert space, then the state space is given by the density matrices on this Hilbert space. And this is actually the standard notion of state in quantum mechanics. So this is indeed a good formalization of the notion of states. And states always form a compact convex space. So you can put a topology on it, and then it forms a compact space in this topology. And also this space is convex, which means that if we have any two states, and a number in the unit interval, then we can take a convex combination like this, and that will again be a state. So that's why it's a convex space. Yeah, another nice thing about effect algebras is that we can model the Bell experiments in this terminology. So what we actually do in the Bell experiment is to each quantum measurement we assign a probability. So Alice chooses a measurement, Bob chooses a measurement, and this gives a certain probability. So informally we have a map from quantum measurements to probabilities, and this map I will call sigma. And then we ask whether this can also be realized using classical measurements. So this classical measurement is like a kind of hidden variable for your model. But measurements and probabilities can be modeled by effect algebras, as we saw before. So for each of the things in the boxes, we have an effect algebra modeling those things. So yeah, we have one for the quantum measurements, one for the classical measurements, and the probabilities become the numbers in the unit interval. So now the question is actually, yeah, we have an effect algebra of quantum measurements and a state on it. And we want to know whether this state factorizes through an effect algebra of classical measurements. So you can think of this as a Boolean algebra because those models classical measurements. And this turned out to be a good model because, as proven by Sam Staten and Sander Uylen, a state is classically realizable if and only if it factors through an effect algebra of classical measurements. Okay, so this is an effect algebraic account of these Bell type scenarios. So now we can go on to defining cohomology. And the idea of cohomology is as follows. So in cohomology we try to define certain functors on a mathematical object that assign abelian groups to it that capture certain properties of your mathematical objects. So the classical example is topological spaces. So we have a sequence of functors H0, H1, H2 that assign to each topological space a corresponding abelian group. And these should contain information about the holes in the space X, or yeah, another way to look at this is by seeing whether loops can be extended to disks. So yeah, if we have a loop in the space, for example a loop like this, then this loop can be filled to a disk. But if we have a loop like this, then it cannot be filled because there's a hole in the way. And this is yeah, an intuition that can be used to define cohomology. So the idea of cohomology is that we take a look at all the loops in the space and look at the loops that cannot be extended to a full disk, that cannot be filled. So for example, this loop would occur in cohomology, but this one would not because it can actually be filled. And in this way, the cohomology group detects holes in the space. So yeah, sometimes it's about extensions. And now we want to define cohomology of effect algebras, and the intuition is a bit similar. So what we want to do is that it provides information about whether a state can be extended to a larger effect algebra. So in our case, the effect algebra of classical measurements. And because cohomology also tells something about extensions, like in the topological case, we also expect that it tells us something about extensions in this case. Okay, so now for the actual definition, it's a bit involved, but I'll try to sketch the main steps. And our definition is based on the cyclic cohomology by Alain Kohn. So originally this was defined for ordinary algebras, but we will do it for effect algebras. And it will turn out that this variation of cyclic cohomology is one of the best suited definitions for effect algebras. So first we take a look at the test on an effect algebra. And a test is a sequence of elements whose sum is defined and equal to 1. So you can think of this as a measurement with, in this case, n plus 1 possible outcomes. So each of the numbers represents one of the outcomes and they are mutually exclusive because they sum to 1. And there are certain operations on tests. So if we have a test of length n, then we can assign a test of length n minus 1 to it by combining two adjacent elements. So, for example, we could define the first element and the second element, or the second element and the third element, and so on. And then in the end we wrap around and we can add the nth element to the 0th element. And this always again gives a test because it still sums to 1. So here's already where the cyclicity comes in, because we actually assume that those numbers are written in a circle, and that's why it wraps around here. So this is a way to yeah, assign a shorter test to a longer test. And yeah, the reason why we look at this is that the tests encode the elements of the effect algebra, and this operation encodes the addition in the effect algebra. So we try to encode as much information as possible of the effect algebra in the cohomology groups, and in this way we encode the addition. Yeah, now we can look at cocycles. So a cocycle is a map from tests into the real numbers that satisfies this property. So it's again like a kind of cyclicity property. So if we take a cyclic permutation of those things, then it should give the same value up to a sign. This condition may look a little bit strange, but let's see what it does when we, when we look at it for n equals 1. Then the test consists of just two elements whose sum is 1, and it should preserve a cyclic permutation of those tests up to a sign, so we get a minus sign here. But if we have a test, then these two elements sum to 1, so that means that B should be the complement of A. So actually we have a formula like this, and this basically says that the cocycle preserves the complement, so it sends a complement to a minus sign. So by looking at the operations on tests, we encoded the addition of the effect algebra, and by looking at cocycles, we encode the orthocomplement of the effect algebra. So in this way we get more information. And then the operation on tests can be dualized to operations on cocycles. Because if we have a map from Tn to Tn minus 1, then this is a kind of dual, so we get that from n minus 1 to n. That means that we have those sets of cocycles and lots of maps between them. And then we can take an alternating sum over these maps. So for example here we would take d0 minus d1 plus d2. And yeah, there's a bit of a technical reason for this, because this is something that's commonly done in cohomology. You always need those alternating sums. So now we have a single map between all those sets of cocycles. And then we can define the nth cohomology group as the kernel of one of these maps, divided by the image of the previous one. So for example, the kernel here lies in here, and then the image of the previous one lies in here, and we can always look at the quotient of these two. So this is in fact guaranteed by this alternating sum, that we can always take the quotients. Okay, so this definition may look a little bit complicated, but so the main idea is that we encoded as much information as possible of the effect algebra into the cohomology group, so at least we encoded the addition and the orthocomplement in it, and that's why it contains a lot of information about it. So let's look at an example. So the simplest example of an effect algebra was the unit interval 0, 1, and it also turns out that its cohomology is very easy. So in degree 0, its cohomology is the real numbers, R, and in all higher degrees it's 0. So this is actually one of the easiest set of cohomology groups that you could get. And then for a Boolean algebra, it's also given by a vector space over R, which has this binomial coefficients. So this is a bit like a torus in ordinary topology, because yeah, if you have a topological space in the shape of a torus, then its cohomology groups are also given by binomial coefficients. So you could say that the power set is like an effect algebraic version of the torus. So these are some simple examples, and it turns out that there are certain techniques to compute the cohomology of many finite effect algebras by decomposing them into building blocks and using certain techniques from homological algebra. So in fact, while the definition looks complicated, there are some powerful techniques that can be used to compute them in a relatively easy way. That's one of the nice things about these cohomology groups. Okay, let's look at cohomology in low degree, so in particular to the first cohomology group, because this one turns out to be related to the state space of an effect algebra. The state space is always a compact convex space, and hence it can be embedded into a vector space over R. And there's always a smallest vector space in which it embeds. For example, the circle is a compact convex space. It can be embedded in many vector spaces, but the smallest one in which it embeds is R2. And now it turns out that the smallest vector space in which the state space can be embedded is exactly the first cohomology group. So this gives a more concrete description of that group, because yeah, the definition was quite complicated, but in fact it's just the smallest vector space in which the state space can be embedded. yeah, the only thing is that we need a certain technical condition on the effect algebra, so it should be finite, and it should have enough states. And having enough states means that the states determine the elements of the effect algebra. So if two elements have equal value under all states, then the elements must be equal themselves. Yeah, and this commutative diagram is a formalization of the property that it's the smallest vector space, which is can be embedded. Okay, so yeah, we actually have a nice characterization of this that's easier than the normal definition. Okay, now let's look at some applications to Bell-type scenarios. So for this we take a state on an effect algebra A, and you can think of this as the Bell state. So in the Bell experiment, there is an effect algebra that models the measurements in the Bell scenario, and then the probability table was given by a state, because this probability table assigns to each measurement a certain probability, and it's in such a way that it forms a statement. And then we want to know whether this is classically realizable, and as we saw before, it is classically realizable if and only if it factors through an effect algebra that represents classical measurements. In other words, a Boolean algebra. So that means that we have a Boolean algebra that makes this diagram commute. And now we want to know if there is a cohomological criterion that tells us whether this is the case. And yeah, for this we look at the it's a connection between the state space and the first cohomology group from the previous theorem. So there is an embedding from the state space into the first cohomology group called I. Furthermore, there is a connecting homomorphism from the first cohomology group of A into the second cohomology group of B of the Boolean algebra. So actually this should be a relative cohomology group. Yeah, I don't really have time to define relative cohomology groups in all details. But if you don't know what it is, then you can just think of this as the second cohomology group of the Boolean algebra B. Now if you compose those two maps, then the state sigma, so the state that we could think about as the Bell state, is mapped to a certain cohomology class in the second cohomology group of B relative to A. And this one turns out to determine whether sigma factors through a Boolean algebra. So we have this condition. So if something factors through a Boolean algebra, then the corresponding cohomology class is 0, but unfortunately the converse doesn't hold. So this is similar to what we got in the topological model of contextuality. There you also have an implication in one direction, but not in the other direction. So you may sometimes obtain false positives. So it may happen that the cohomology class is 0, but still the states may not be classically realizable. So that's a bit unfortunate. So what can we do about this? So how can we get rid of false positives? Well, there is a way to do this by adapting the definition of cohomology. So the problem with our previous definition of cohomology is that it involves a lot of information about the effect algebra. So it involves the addition and the complements. But effect algebras also carry an order, and we didn't take this order into account. But this turns out to be crucial if you want to look at realizability. So that's what we will now try to do. We will try to put the order into the definition of cohomology. So the main step in defining the cohomology was looking at this set of cocycles. And then what we will do is we will replace it by a new set of cocycles, which we will call the ordered cocycles, indicated by this subscript inequality sign. And to get to those ordered cocycles, we do not only look at maps on the n tests, but we also add a map on the n-1 tests. And then we add this criterion to it. So recall that this delta was an alternating sum over boundary maps, and the boundary maps were the maps that combined two adjacent elements by adding them. And then if we have a map on the n-1 tests, then by applying delta to it, we get a map on the n tests. So we can compare the map phi with the map delta psi, and then we want to require that phi is greater than or equal to delta psi, and in that way, we take the order into account. And then if we make some more modifications along the way in the definition of cohomology, then we end up with a new definition of cohomology groups, which I will call order cohomology groups. Now, for the original cyclic cohomology, we had this condition, and if we replace the cyclic cohomology know that a state is classically realizable if and only if it factors through a Boolean algebra, and that happens if and only if this cohomology class in order cohomology is greater than or equal to 0. So in this way we get a nice characterization of realizability without any false positives. So this is quite nice, and so yeah, let's look at some conclusions. So effect algebras can be used to model contextuality scenarios and to model classical realizability. And then we have two kinds of cohomology, namely cyclic cohomology and order cohomology. Cyclic cohomology has the advantage that it's relatively easy to compute, but we get those false positives. And order cohomology is more difficult to compute, but we do not get any false positives. So it's still a bit of a disadvantage that it's more difficult to compute because we have this order relation on it, and that means that we cannot apply standard techniques from homological algebra to compute those proofs, even though we could do this in the case of cyclic cohomology. So maybe this would be a nice opportunity for future research to try to generalize techniques from homological algebra to the ordered setting in such a way that it also becomes easier to compute, and that would give a really useful criterion for studying contextuality using cohomology. Okay, thank you.
Questions? So, for the order cohomology, can you see the state space as, so the first order cohomology group, can you see its relation between the state space as some kind of minimal ordered structure?
Yes, in fact the relation is easier in this case. So if you look at order cohomology group, then the first cohomology group consists of all maps from your effect algebra into the positive real numbers. And if you have a map into the positive real numbers, then you can just rescale it, so you can normalize it in such a way to obtain a state. In fact the connection is even closer than in the case of cyclic cohomology.
Do you have any concrete example on how to apply such a method to actual models?
So I've mainly computed cyclic cohomology so far in several cases because there are some nice techniques to compute it. But there you still get those false positives very often. For example, in the Bell scenario, you actually get a false positive, so then cyclic cohomology is not very useful. So it might be nice to look at some examples in the case of order cohomology, but this is still, I still don't really know good techniques to compute it except in very easy cases.
You said the state space could be embedded in the vector space, this H1. Is that H1, is it an order unit space? Because there is a universal construction to embed.
Yeah, so it's at least an R vector space.
Oh, it's a Basel space. Oh, I see. The dual.
When you say it's difficult to compute, does that mean you don't really know a good algorithm, or the algorithm is very expensive?
It's mainly that the algorithm is very expensive, because if your effect algebra is finite, then the collection of tests is also finite, so you could just use a computer algebra package to compute everything. But those set of tests tend to become very large even for low values of n already. So except in the case of very small effect algebras, it's just very expensive to compute. Well, for cyclic cohomology, there are techniques to compute it without using this whole framework of tests.
First I want to say what I'm interested in, because maybe I'm trying to put it in a question that it's maybe more easy to answer. Okay? I'm interested in what is the physical meaning of having this new restriction, or this new structure. You see?
So which restriction?
No, the structure of the order.
Okay.
Okay. But to put it like in something that maybe is more easy to answer, I would like to know what it means on this relational database empirical model that has Abramsky. How you will see in this picture what you are adding. This is true.
Okay, yeah, I'm sorry, but I'm not very familiar with this relational database framework. But so in the case of effect algebras, the order can be thought of as a kind of implicational order. So if you have a logic, then you often have an implication in it, and this order can be thought of A is less than or equal to B if and only if A implies B. That's a kind of logical interpretation.
Yeah, probably this should be better, maybe discussed further offline in the break. Is there one? Chris, you have
So you showed us 3 examples of effect algebras, the unit intervals, the Boolean algebras, and the effect algebras for the effects on the local space.
Yes.
And you computed the homology of the first 2.
Yeah.
Do you know anything about the third?
Okay, so cohomology of infinite effect algebras is very difficult to compute in general because yeah, the set of tests need not be finite anymore. So yeah, I don't even know an algorithm for it. Yeah, it turns out for finite algebras I can mostly compute it, but for infinite algebras I can only do it in very easy cases. So I do not know yet what the cohomology of the effects on the Hilbert space would be.
Okay, there are more questions, but I think in the interest of time, maybe they could be